That should work. Okay, I used to be at the University of Florida, but it was too cold, so I'm now at the University of Central Florida, which is in Orlando. And I want to first thank you, Jose Miguel, for inviting me to give this talk. And I'd like to tell you about my collaborators on this work. Jan Fernandez, who's also at the University of Central Florida, Mike Kelly, who's at the University of Maryland, and Javier Licandro, who's here. And I also want to thank the IAC because I've just finished 11 months of a great year of research here. I'm going to give you an outline of what I'm going to tell you about. I'm going to give you a quick introduction about solid minerals and organic material in comets. I'm going to focus, we have a lot of observations in the mid-infrared of comets. And I'm going to focus on two case studies. One is an Oort cloud comet, which is Hale-Bopp, and the other one is a Jupiter family comet, which we believe all the Jupiter family comets come from the Kuiper belt, or the trans-Neptunian region. And that is comet 9P Tempo, which was hit by one part of the Deep Impact spacecraft in 2005. I'm going to tell you about the observed bands that we have on these objects, and about what that tells us about the grain composition. I'm going to tell you a little bit about the diversity among Jupiter family comets and between Jupiter family comets and Oort cloud comets, and what we can learn from that. Then I'm going to compare comets with other objects. I'm going to discuss the similarities between some of the comets and some of the circumstellar disks, and what we can learn from that. And I'm going to tell you a little bit about the connection between comets and primitive asteroids, which we believe also have a trans-Neptunian origin. So then I'll tell you what should the main targets for comet observations with CanariCam should be, which are basically Jupiter family comets, which are predictable. They're faint, but they're relatively faint, but predictable, and many of them very reachable with CanariCam. The new comets will be targets of opportunities because they usually get discovered only a few months or a few weeks before they become very bright. And some of them come near the Earth, and they give us other opportunities. And I dare to infringe on Rafa Revolo's territory and suggest that we should observe circumstellar disks with the temporal coverage, because it has been suggested that the spectra of some circumstellar disks can be explained by very large active comets that are just happen to be active at that time. And then I'll give you a quick set of conclusions. So to give you a better visual of what I'll be talking about, this is comet Hale-Bopp in 1997, taken from the Arizona desert. This is comet 9P Tempo right after the impact, taken by the spacecraft, an image taken by the mothership when the projectile hit the comet. And we know from mid-infrared observations of comets that they can be very diagnostic of solid grains in the comi of active comets and on the surface of low activity or inactive ones. The surface features from objects that are not active, comets that are not active, and asteroids, it's a little bit of a surprise. We didn't expect to see such spectral contrast. But these observations tell us about the minerals in the comets, which include mainly silicates. They dominate. The silicates dominate the composition of the minerals in the comets. But we have also detected carbonates, metal sulfides, and even ice, water ice. And they also tell us about the organics. PAHs and other organic components have been proposed to explain some of the spectral structure. So I'm now going to go to the case studies. Slow me down if I'm going too fast, but I also want to make it to lunch. But please, I mean, do interrupt me like you did with Charlie, because this is a workshop after all. So my case studies are comet Hale-Bopp, which is the Oort cloud comet, and comet P Tempo, which is a Jupiter family comet. And as I said, Jupiter family comets come from the Kuiper belt, or the trans-Neptunian region. And so I'm going to tell you a little bit about the observed bands and what those bands tell us about the detected species. And I'm going to tell you about the differences among each of the two classes, Jupiter family comets and Oort cloud comets, and between them. So the observed bands. I'm going to show you an ISO infrared space observatory spectrum of comet Hale-Bopp, which happened to be bright, and the comet was kind enough to be around when we had an excellent observing platform in orbit. And then I'm going to tell you about the Spitzer spectra of 9P Tempo before and after impact with the spacecraft. So here's the mid-infrared spectrum of comet Hale-Bopp taken with ISO, and in it the spectral structure identified with the silicates: amorphous olivine, crystalline olivine, magnesium-rich olivine, which is called forsterite. So we have a number of peaks that are identified in this, just as a way of illustrating the type of structure that you see there. Then I have the 9P Tempo spectrum before, which is in the bottom, and then after impact. And notice the sharp difference in the spectrum. The one before was basically a black body. It had very little spectral contrast. And after impact, we see the very strong peak in the 8 to 13 micron region due to silicates and the structure within that peak. And then more structure at longer wavelengths, of which we've been able to model, and I'll tell you more about those models later. Yes?
Are those normalized, or is that the actual?
They're normalized, yes. It's just that I had to modify a little bit the figures so that I could, anyway. But go ahead, yes.
Sorry. The after spectrum, where would it hit?
I think the after spectrum was not normalized. The lower spectrum was normalized to 1/10.
Oh, so okay. So okay.
Yeah.
Thanks.
That gives you an idea of the flux. Anyway, so what's interesting here is that we had a Jupiter family comet with an ambient coma that was showing us essentially no structure. So you would have thought that this comet had no silicates, which is one of the explanations. But instead, once you hit it with a projectile, it freed up all this dust, which had silicates, with crystalline silicates, amorphous silicates, all kinds of structure that we found that is in many ways very similar to comet Hale-Bopp, and in some ways also very interestingly different in some specific details that I'll go into in a second. So we observed all these bands. So what species produce these bands? This is work by Casey Lees and collaborators, and they did a very detailed model of the emission from the comet 9P Tempo after the impact, and that is the upper spectrum. Those are the observations. So they have identified specific features due to olivines, crystalline olivine, crystalline pyroxene, hydrated silicates, amorphous silicates, sulfides, amorphous carbon, water ice, and in order to show in more detail the minor components, not just the silicates, but the minor components, they have subtracted the silicate, all of the silicate components, and so that's the spectrum. After this, they subtracted the silicates, and you can see in a little bit better detail how incorporating water gas, water ice, and the minor components like the sulfides and the carbonates make the fit to the spectrum better. This is much trickier. The identification of these features are a little less accepted, but they make the fit of the model better. Now, CanariCam won't be able to get this much wavelength coverage. We're going to be concentrating mostly in the 10 micron window, but this gives you an idea. The good thing about the 10 micron window is that it's got the most information about the silicates and about the other components. So here is from a recent review by Mike Kelly and Diane Wooden, a summary of what was discovered in comet 9P Tempo and the surface area that each of the components had. So you can see that the dust is dominated by the olivine and the pyroxene, and then you have all these other components, including the likely detection of PAHs over here. We don't have a laser pointer. Is it? Thank you. Thank you. So we have the PAHs which have been proposed. It's somewhat controversial, but there seems to be strong evidence for them. Okay, so now let me discuss briefly for you differences among and between Jupiter family comets and Oort cloud comets. Remember, these come from two reservoirs. These are the Trans-Neptunians, and this is the Oort cloud is the new comet. Here we have now this is in relative flux, and we have again, the pre-impact tempo 1, the post-impact tempo 1, and the Hale-Bopp spectrum. They have similar morphologies, but when they're analyzed in detail, we find interesting differences between these two and other comets, but I'm using these two as examples. The grain properties, the emission that you see in the mid-infrared is affected by the composition of the grains, by their size, and I'm going to use porosity as a way of indicating basically the shape and the amount of empty space that they have in them. And so these three characteristics determine the spectrum that you see. And so porosity appears to be mainly responsible for the different strength in the silicate emission feature among comets. Most Jupiter family comets have weak emission features. The strongest emission features among Jupiter family comets are about equal or a little bit less than the new comets and the Oort-Cloud comets. But we think that this is not due to a difference in composition, but it's a difference in porosity. But there are compositional differences that are very, very clear and are also very interesting. And so let me spend a little bit of time on that. So, yes, please.
Thanks. So is there a particular sense in which it goes of increasing porosity does what to the silicate features?
Increasing porosity increases the strength of the silicate features. Yes. So in terms of different compositions, not just porosity, we have some cases where the compositional differences are clear. And again, this is one of the reasons why I chose these two objects. There's an interesting contrast between magnesium-rich crystals in Hale-Bopp, for example, and in most of the Oort-Cloud comets, we have magnesium-rich crystals. So these are crystalline olivine and pyroxene, which are magnesium-rich. And in comets like 9P Tempo, actually in 9P Tempo, because this is the only Jupiter family comet that we have observed in this much detail, we have that the crystals are dominated by iron-rich silicates. And so we're interpreting it as indicative of the degree of hydration in the nebular region where these objects formed. And this is because when you hydrate silicates, the first ones to hydrate will be the iron-rich. So the magnesium-rich silicates are the ones that resist hydration the longest. So it is possible that you have considerable hydration where 9P Tempo formed, and considerable less hydration where 9P Tempo formed, and considerable hydration where the Oort-Cloud comets, typified by Hale-Bopp, formed. Questions about this? Yes, go ahead.
Did anybody take spectra of Holmes, the comet that had an outburst? That was a Jupiter family comet?
Yes, and I believe that there's Spitzer spectra. They're not published yet. But I'm almost sure that Spitzer took a very nice time series observations of Holmes and watched the whole outburst occur. But they haven't been published. So I don't have access to them yet. Only the PI does. And so some remaining issues are how common are iron-rich silicates, anhydrated silicates in Jupiter family comets? That's one of the questions that we would like to address with CanariCam. And the other one is does the observed diversity arise from primordial conditions or evolution? That's a harder question to answer, but of course we're going to need to sample a larger number of both Jupiter family comets and of Oort-Cloud comets with CanariCam. So let me jump to my third item, which was interrelations. So first, I'm going to discuss the similarities between some comets and some circumstellar disks, because not all comets in the mid-infrared look like circumstellar disks, and the ones that don't look like all circumstellar disks. Only some circumstellar disks show this similarity in the silicate emission features. So here's a paper by Beichmann, where they took the Spitzer spectra of the excess emission from a K-type star HD 69830, and they normalized comet Hale-Bopp to the same temperature as this excess from the star, and you can see a remarkable similarity. You basically identify all of the same crystalline features in this circumstellar disk as you do in comet Hale-Bopp, which led these people to propose that it was either many comets that happened to be in a kind of a bombardment at the time or active near the star, or the presence, which they favor, the second explanation, which is the presence of a very large comet that happens to be active and dominating the excess from that star. And so what can we learn about circumstellar disks and our own solar system from the mid-infrared similarities? Well, the fact that we have crystalline silicates in circumstellar disks and in comets means that but not in the interstellar medium. The crystalline silicates are absent in the interstellar medium. So somewhere between when they formed in late-type stars and when they go into star formation regions, they get processed, and they get processed to about 1,000 degrees Kelvin at some point. In the case of comets, we believe that this happened early during solar system formation, near the sun, and that annealing of the amorphous silicates happens, and then it gets incorporated into the comet, because you cannot raise the temperature of a comet to 1,000 degrees and still be a comet. It would be just a rocky leftover, but all the ices will be gone. So this material has to be crystallized somewhere near the sun and then transported out. So this likely occurred in the disk during the early stages of solar system formation, and the samples from the Stardust spacecraft that are being analyzed, both in terms of crystalline structure, composition, and isotopic composition, support this view. And so comets are diagnostic of disk conditions and of processes. So what I'm telling you is this. Somehow, where comets formed, they got some crystalline silicates that had been processed near the sun and got transported out. And we believe that something similar is occurring in other circumstellar disks. And Rafa Revolo will tell you more about that. So there's diversity. Maybe not. No, okay, well, I'm glad I told it then. Okay. And then we have diversity of circumstellar environments. They tell us about the spatial and temporal information about the disks, and diversity of comet composition, primordial, evolutionary, both. And this I'm going to only just mention very briefly. We have interesting connections between primitive asteroids, trans-Neptunian objects, and comets. In a nutshell, what's happening here is that dynamical models of what's called the late heavy bombardment tell us that D-type asteroids in the outer asteroid belt are all trans-Neptunian objects that got moved in. So in other words, they're inactive comets. And that is basically it's been confirmed by our near and mid-infrared observations of cometary nuclei and primitive asteroids, which are consistent with these dynamical models. So we're finding that comets look a lot like these primitive asteroids. And here are Spitzer spectra of a D-type Trojan asteroid. This is our Spitzer spectrum of comet of 944 Hidalgo, which is the most likely asteroid to be an extinct comet, actually quite strong evidence dynamically. And here's a main belt asteroid, and you can see that this structure here is very similar between the D-type and the extinct comet candidate, but it's almost gone in the main belt asteroid. So we found a very diagnostic tool to study what may have happened in the early solar system. You'll get your chance if there's some. I have my minute and a half left. So what I'm saying is the late heavy bombardment, this period of heavy bombardment on the moon and the Earth, has been explained in a way that tells us that the active comets and the primitive outer belt asteroids are similar objects. And again, Javier will tell you more about this. So the targets of CanariCam. Jupiter family comets and extinct comets, which we can study this abundance of iron and magnesium and hydrated silicates and test dynamical models. New comets, which will be targets of opportunity to study diversity. And if I may propose that we do some temporal coverage of objects like HD 69830 to test this model that it was produced by a single active comet, and therefore the strength of those features should be dying down with time. And these are my conclusions, which is essentially what I just told you. Thank you.
Can you go back to the slide of the where you show the spectra? Go one more. This one.
Okay.
How do you explain this feature? I mean, this is the feature you see in the Trojan asteroid and the extinct comet candidate. It should be like grains in space, not on the surface.
Yes, so this is a nice surprise. We still don't know quite what's going on in there, but it's very diagnostic of the silicate composition. So we're delighted. So yes, on a solid surface, you should not see this kind of spectral contrast.
The spectral bump at 10 microns.
Yeah. And actually, there's structure here that is quite interesting. But no, we don't know exactly why. We think that there's very fine dust on a matrix that is transparent to the mid-infrared, and that's what's happening, but we don't know.
Let me remind you that we have some time set aside this afternoon for discussion, so we can bring up all the questions later on. And now we better go to the cafeteria where we have lunch prepared. Thank you very much.
Good. I wanted to show the beta pic detection.
The classic.
Yeah. But I thought with this little time I have to focus.
Nobody would